Request Professor Sujeet Sinha to start his presentation. I'll request you please to complete your presentation in 18 to 20 minutes time and 3 minutes time for the questions. Please.
Thank you, Dr. Singh, for very kind introduction. And thank you very much for coming to this talk. So today I will talk about bio-tribological studies of a very special polymer that we have found. It's a polymer which we have converted into some composite. So this is the called Structalit. The Structalit is a commercial polymer, but it is basically epoxy mixed with calcium carbonate. So I will show you some results on this for application, which is basically hip joint application. So for the hip joint material, that is the kind of application we have considered. So before I go into, and by the way, co-author is Jaswant Hirwani, who is sitting here. So before I start, I would like to acknowledge these individuals that have contributed at several levels. And also I would like to acknowledge this ES and DST grant. And another thing is, I would like to say there is no conflict of interest in this work because the work has been all funded publicly. So there is no private funding here. So with that acknowledgement, I will start.
Yeah, I'm going to start.
So human joints, we have in our body we have several joints, and these joints are extremely important, of course, for our functioning of our body. But there are few joints which we may say that they are even more. So these joints are load-bearing joints. That means our body will carry the body weight on these joints, and therefore it is very important to look after these joints. Of course, always good that we don't have problem, but if there is problem, then how do we solve that problem? So our material and our composite is more focused on the hip joint, and hip joint and knee joint has got a lot of similarity, but there are some differences as well. So therefore, I would like to focus entirely on the hip joint. It's what are the requirements and how we can find a better alternative material for implants. Now, about the hip joint, if you see, these are the kind of motions. They are different motions, and these motions are can be quite complex, but they have been simplified into 3 different types. So first is the extension and flexion. So as you can see, the extension is going in the backward, flexion is going the forward. So then adduction and abduction, so basically going this way and then coming this way. And there is another motion rotation. So these 3 kinds of movement will cause what is called crisscross or multi-directional sliding at the hip that is here. So there will be a crisscross, that means the sliding will not be just in one direction. Normally with the knee we have only one direction sliding, but in the case of hip it is multi-directional because we are unique in that we can move our leg in different directions, and that gives crisscross multi-directional movement. So the problem of hip joint is osteoarthritis. So osteoarthritis is basically degradation of our joint, and our joints are working very beautifully because of the articular cartilage we have. So on the top of the bones we have articular cartilage, and these articular cartilage basically provide us very good lubrication, and that's why when our joints are working good, we don't feel any problem, any pain or anything. But with age, people get problems. So it is quite common, many people will have knee problem or hip problem, or sometimes because of some accident or because of some overuse of the joints. Let's say some sports personality, they will be overusing their joints. So in that case, they might suffer. So this is a health issue, and it almost like 10% of statistics shows that 10% of US population will undergo this surgery for replacement of the hip. That means artificial hip. And looking at the artificial hip, it has got three main points, main parts. So one is the femoral head, which is implanted in the thigh bone. Okay? So as you can see, this is on the thigh bone side, and there is a acetabular component here, which is fixed to the pelvic bone, and there is a liner. Liner is made of polymer, and liner is basically fitted to this acetabular component. So this is a plastic liner. This is made of UHMWPE. So UHMWPE is basically polyethylene. So this liner is fixed with this part, but there is a movement between the femoral head and the acetabular cup. So there will be some sliding, and as I said, it will be multi-directional sliding. So because of this sliding, this becomes a tribological issue, and our main focus is on this. So if you look at the cartilage is a very efficient in terms of tribology. It gives an extremely low coefficient of friction, and wear is almost nowhere. So looking at the cartilage, it has got hierarchical structure, and it is mainly made of type 2 collagen and many types of glycoprotein, hydroxyapatite. These kinds of materials basically provide structural strength, because you need some structural strength. And then there are lots of macromolecules which will provide the lubrication. And this lubrication is water-based. So that means all these lubricant molecules are basically in a water situation, aqueous environment. So there is no oil here. So this is the complexity of the lubrication of cartilage, which people are still trying to understand, and we have conducted some molecular dynamics simulation to understand how the lubrication of our natural joints work. If you simplify it schematically, you can see that this is a knee, represents the knee part, and here there are two cartilages sliding against each other. Same thing will happen in the hip as well. And this is inside a cavity, and it is covered by a synovial membrane, and the lubricant is called synovial fluid. So synovial fluid is the lubricant, which is all around here. So whole thing works within the synovial fluid. And if you look at the cartilage, the top part of the cartilage is something like this, which is called superficial zone. So here, basically it is a graded material. That means the property changes as you go from the bone side to the top surface of the cartilage. So in terms of elastic modulus, hardness, it changes. And on the top surface, we have got proteoglycan, different types of molecules, for example, hyaluronic acid, lubicin, lubricants. So these molecules which are provide the lubrication. So schematically you can say that the top surface of the cartilage is something like this, where we have got all these collagen network, type 2 collagen network with lubicin, HA and phospholipids all around. So some of the molecules like phospholipids are charged molecules. That means they have got, although they are overall they are neutral, but they have got positive and negative charge, so that they can attract water molecules for lubrication. And this can be shown schematically here, which is called like a bottle brush type. So here the protein molecules are distributed here, and they have got charge, negative and positive charge, and they attract water molecules, and therefore they can provide water lubrication. So this is the whole very simplified version of how our joints work, but there are a lot of complexity which we are still trying to understand. So looking at the hip implant parts, so basically as we have understood, it's femoral head, the UHMWP liner and the acetabulum composite. So these are the three parts. And the actual sliding part is the metal sliding against a polymer, which is UHMWP. Other than tribology, there is also another issue which is called range of motion of femoral head. That means how much it can be moved. So the more it can be moved, the better it is in terms of stability. Okay? Otherwise, there is an issue of dislocation. So dislocation is another problem, because even after surgery, if implants have been implanted in the body, but if it gets dislocated, then obviously it is not good and the patient has to go for another surgery. So range of motion can be increased if we make the liner thinner. And we can make the liner thinner if we can improve its mechanical strength, because ultimately the weight, it has to take the weight of our body. So to satisfy that condition also we can improve the material. So UHMWP has got lower strength, so if we can improve that, then we can make it better acetabulum compound. So basically UHMWP has been the polymer part for hip and knee prosthetic joints for quite some time. Cross-linked UHMWP is used because it has got better mechanical property. However, it has worse lower wear property, as well as fatigue property is also because of oxidation. So vitamin E has been added into cross-linked UHMWP to improve its antioxidant property, and therefore the wear and the fatigue properties have been improved for UHMWP. So these are the solutions that people have tried, but still you can find these kind of problems and the failure. The wear particles come out of the material, as well as these kind of fractures will happen, cracks and fractures, and some decoloration you can see, which is like oxidation. So all this problem happens, but we will be focusing on the tribological issues like wear and friction. The wear particles that come out of UHMWP is actually not biocompatible. That means the body does not like it, and what happens is basically our body has got macrophages. So macrophages are molecules which basically will eat up anything wrong, like bacteria or something foreign body is basically eaten up by macrophages. So in this case also, what happened, macrophages will try to eat up the debris particles, and obviously it will not be good for our body. It will show some inflammation and some problems. So that's the reason why we do not want debris particles, we do not want wear particles. So we will try to reduce the wear of the material as much as possible. So here we have tried epoxy, basically two types of epoxy, SU8 and Structalit. Both are epoxy, but they have slight difference. Structalit has got calcium carbonate already inside it. So we have made composites of these two types of epoxies with UHMWP particles. For example, 35% UHMWP particles we have added. So basically I will be talking about these two, and mostly I will focusing on Structalit because that's the focus of today's talk. Looking at the Structalit with UHMWP composites. So basically Structalit has got calcium carbonate, so we have checked in the ACM and we have found that yes, there are some calcium rich area which indicates that calcium particles are there. Because this is a commercial material, we wanted to make sure that this is exactly what they say. So here you can see some calcium particles, and also once we add UHMWP particle, we find that there is a very good bonding between UHMWP particle and Structalit. So this bonding, later I will show you whether it is chemical or not. But we believe that this is more like a physical bonding between the two. So straight away I will show you the data. Basically SU8, and here with hardness, 7% hardener, and this one is for SU8 with UHMWPE particles. So as I said, 25% UHMWPE particles, and this is Structalit with UHMWPE particles. So in general we can see that once we add UHMWPE particles, elastic modulus has come down, okay? But overall Structalit has better elastic modulus as well as strength, better than SU8, okay? Even though both are epoxy, but Structalit has better strength here, and this strength and modulus are much higher than the original material, which is UHMWPE. So here we are trying to replace UHMWPE with these kind of composites. So I am just showing you some of the bulk mechanical properties because those are also important in tribology. Hardness, again hardness also we can see that Structalit has better hardness, but after we add UHMWPE particle, hardness will come down. So this is, we have seen, and the reason is because UHMWPE is a softer material. So that is the reason. Now, looking at the coefficient of friction, all in dry sliding. So basically we get, for the composite, we get coefficient of friction lower than 0.1 for both cases, for SU8 as well as for Structalit. Less than 0.1 is a good in terms of coefficient of friction, because UHMWPE will give you coefficient of friction of 0.16 or 0.15. So we are slightly better here. And we also conducted specific wear rate. So wear rate also has come down quite considerably for the composite in both cases. And Structalit composite has better performance than SU8. But these are all dry tests. But for hip joint application, we always conduct in a lubricated sliding. So in dry test, we saw that although the bonding is very good, but we can find some of the places where there is a crack initiation. So these are ACM pictures, as well as we can see that there are some UHMWPE flakes or particles attached to the matrix, which is sort of covering the surface here. So this, another important thing is about the bonding between UHMWPE particle and the matrix. Matrix is SU8. We find that there was no chemical change. So there is no chemical bonding. So the bonding is basically a physical in nature. The UHMWPE particles basically gets covered by the cross-linked epoxy. So this data basically shows the variation of the mechanical properties for different percentage of UHMWPE. So this we did as an optimization, and we found that perhaps 24% of UHMWPE particle is good composition for Structalit. And more important is this one, tribological results, coefficient of friction and specific wear rate. So this experiment was conducted in diluted bovine serum. Bovine serum is a lubricant that is used for this kind of bio-tribological experiments. It is not exactly what we have in our joints, synovial fluid, but it represents, it is quite close in that way. So we find that Structalit with 24% UHMWPE gives a very low coefficient of friction, and here we have compared with pure UHMWPE, which is the material we are trying to replace, and even better than UHMWPE. And in terms of specific wear rate, also we find that 24% of UHMWPE particle in Structalit gives better property compared to pure UHMWPE. So here we see that there is some scope for new material, and here you can see after the wear test how the surfaces look like, and you can clearly see that UHMWPE particles here, as well as you see some extension of UHMWPE molecules, which basically try to cover the surface and protects the surface. Okay? But in some cases, we do see some of the cracks here, crack development between the particle and the matrix. So which could be the reason for wear, but in general we see that surfaces are very smooth and very well covered. So we just thought about what is the mechanism of friction, why friction is less for the composite compared to UHMWPE itself. And basically we understood that if you have got two stiff material or high strength material, for example, these two sliding against each other, and if there is a thin layer of lubricant, low shearing material in between, then this condition gives us low coefficient of friction compared to a situation where you have got stiff and soft material. Even though the soft material has got low coefficient of friction by nature, but in this case the contact area is more, and also we see that the volume of dissipation, energy dissipation is increased because of its softness. So more amount of material will be deformed, and therefore there will be more energy dissipation here. And that's why the coefficient of friction is large in this case. And when you have got two stiff material together, in that case you have got a lot of brittle fracture happening at the interface, and again friction is high. So we are in this situation where friction is low because two hard materials with a soft interface at this point. The 3D profile of these two surfaces again tells us similar things what the CM picture has given. So in the case of pure UHMWPE, we can see a lot of plastic deformation, lot of bulk deformation, which increases the friction. Whereas in the case of this 24% UHMWPE with Structalit, we see that these UHMWPE particles cover the surface, and we end up with a very, very smooth surface, a low shearing smooth surface, and that gives us low friction. Further on, we conducted a test where we have added a lubricant, bio-lubricant. Hyaluronic acid is part of our joint material. So we have added actually and made a further improvement in the composite. And this picture, this slide shows us the kind of test we have conducted. Okay? So this is called multi-directional sliding test, where a pin rotates on its own axis and basically the disc reciprocates. So there are two types of motion. One is the rotation of the pin on its own axis, and then translation. So this gives us situation of multi-directional sliding. So this is how the specimen looks like. And today Jaswant will show you much more about this equipment, but I'm just showing this short video on this one. Here you can see that the load is being applied using a fulcrum. This is the place where the pin is rotating on its own axis and the disc is reciprocating. So you've got very good multi-directional sliding test. So after adding HA, so hyaluronic acid, which is a bio-lubricant, we have tried 0.2%, 0.5% and 2% just to see what kind of improvement in tribology we can see. And this gives us hardness results, and generally we don't see any kind of trend, but we can say slight reduction in the hardness because of the lubricant. And here is coefficient of friction. So if you add hyaluronic acid, HA, in this composite, then coefficient of friction is further reduced. So this is the original UHMWPE, and we have come down to 0.05. And similarly, we can find in terms of wear rate also, we have got much more improvement. So basically, this composite where we have used epoxy, Structalit as the matrix, and UHMWPE particle plus HA as the lubricant, and we get a very good result in terms of both friction and wear. So this is something we are still working on. These are some optical microscope. So we are still working on these results. So I hope in the future we will have more confidence about this composite. But this composite shows some good potential. So here I will summarize. So many efforts have been made towards finding a solution for hip and knee joint prosthetic implant materials going beyond pure UHMWPE or cross-linked UHMWPE. Use of Structalit composite with UHMWPE and hyaluronic acid as figures have provided very promising results in the multidirectional wear test. And both reduction friction and specific wear rate are lower than those of pure UHMWPE. So that is a good achievement for us. So that's all. Thank you very much for your attention.
Thank you, Professor Sinha, for your excellent talk. Any questions?
So Professor Sinha, again, a wonderful talk. I was wondering if you have any comments on the wear debris, if there was any study conducted on the wear debris of the different composites, and any observations on that front?
So yeah, we have not been able to study the wear debris yet. So this will be our next. So right now we have established this wear test, which itself is quite complex here in this case. So we can conduct the wear test using mass loss method, but we have to look into what kind of wear debris particles are being created, and we have to study that. But thing is, we are almost near. Almost close to zero wear. So, in fact, it goes negative. That means we are in a situation where there is a little bit of mass increase. And mass increase is because some proteins get attached and some of the liquids migrate inside the material. But the fact is that overall we get negative wear. That means there is mass gain. So, but we have to still look into the liquid and see what kind of wear particles or what kind of protein degradations are happening. So, that is next.
Thank you, Professor Sinha. Now, I invite next.